All right, next up, we're going to talk about formal charge versus valence electrons. You can see the abbreviations there. Both of these are just different ways of counting electrons. If you haven't figured it out yet, in chemistry, it's really the electrons that do everything. We don't change the identity of the atom. We'll never change an argon to, a neon or anything like that, unless you're talking about nuclear chemistry, which is relatively rare. What we're more so talking about is changing the bonding. So messing with the electrons. Both of these are important. And we'll actually later on learn even more ways to keep track of electrons, because each way tells us some more or some different information. So let's take a look at valence electrons. This valence electrons tells us if atoms have the, quote unquote, correct number of electrons, right? And if we have a good Lewis structure, we will have a filled valence shell. Right, most often an octet, but as we know, some elements don't want full 8 valence electrons. But a good Lewis structure, everything will have a filled valence shell. And having this filled valence shell is actually more important than a low formal charge, which we'll get to a little bit later on. So if you're deciding between two Lewis structures, one has a high formal charge, the other one has one has a low formal charge, the other one has a filled valence shell, go with the one with the filled valence shell. And we'll see more examples later on. So that's valence electrons, right? It allows us to count how many, or whether it tells us whether we have a filled valence shell. With formal charge, this is just a fictitious charge. And it tells us if the atom has more or less electrons than its lone atomic state. And in general, we want to get a low FC as possible. So the best Lewis structures will generally have all formal charges equal to 0. So we don't want negative or positive formal charges, but sometimes it's unavoidable. All right, so maybe you took Chem 100 or high school chemistry, and you drew Lewis structures that look something like this, right? Where we've put this positive charge just on the outside and the molecule in brackets, right? Indicating that this molecule overall has a positive charge, but we don't know which atom bears that positive charge. So from now on, this is going to be not good enough. So not good enough anymore. We want to do what's called localizing the formal charge. So we need to localize the formal charge, right? And same thing for like hydroxide. Maybe you've seen something that looks like this, where the negative charge is just put on the outside, right? That's no longer going to be good enough. We're going to go ahead and localize the formal charge. We're going to indicate which atom has that formal charge. And that tells us a lot about the stability of the molecule and the reactivity of the molecule. Usually if a molecule has a charge somewhere, that's going to be the site of reaction. So when we're thinking about formal charge, we count the electrons and we count the charge if all electrons were shared evenly. Right? We know that's not true. We know in a lot of covalent bonds, the electrons aren't shared evenly, but when we consider formal charge, we pretend that they are. So formal charge is equal to the number of valence electrons on the lone atom minus the number of non-bonding electrons, so electrons in our lone pairs, minus the number of bonds. So let's take a look at some examples. So we'll start with kind of our oxygen-hydrogen series. So we've got OH, we've got H2O, and then we've got H3O. There are the Lewis structures to them. What we're going to do now is calculate the formal charges on all of these atoms. So let's go ahead and start off with this oxygen right here. And then using our equation, right, we know that the formal charge is going to be equal to the number of valence electrons in the lone atom. So what I mean is when it's just kind of by itself, how many valence electrons does it have? We can see that oxygen over here is part of group 6, so we'll have 6 valence electrons. So 6 there, minus the number of non-bonding electrons. So it has 3 lone pairs, which is 6 non-bonding electrons. So then that will be minus 6. And then the number of bonds, it's bonded to 1 hydrogen with a single bond. So we subtract 1, and our answer here is -1. So that oxygen has a formal charge of -1. And then the way that you show that is you draw a little negative, and then you generally circle it if you're writing it by hand, just to make it a little bit more clear. Let's take a look at this hydrogen. The formal charge, hydrogen normally only has 1 valence electrons. Here it has no non-bonding electrons, and then 1 bond, it is equal to 0, right? So the hydrogen does not have a formal charge. It is the oxygen that bears the formal charge. So for example, when we were taking a look at the structure here, right, we just said somewhere on this molecule, there's this negative charge. Now we identified that the negative charge is on the oxygen. And when this molecule reacts, it's most likely going to react with that oxygen. All right, next one up, we got this oxygen right here, right? We said the formal charge is equal to the number of valence electrons of the lone atoms. We said that was 6 for oxygen. Here it has 4 non-bonding electrons and 2 bonds. So its formal charge here is 0. The hydrogens, right, 1 electron normally, 0 non-bonding electrons, 1 bond, 0, right? So in this case, we have no formal charges. So you would just draw that molecule as it is drawn right now. Note that I'm drawing in kind of like this bent shape as opposed to kind of just a straight line. We'll learn why later on when we get to shapes. Next up, we're at this oxygen, right? So normally 6 valence electrons in the lone atom. Here it only has 2 lone electrons, right? 1 lone pair, and then 3 bonds. If you do the math there, that's +1. All these other hydrogens, if you think about it, they're all the same, right? 1 electron on its lone state, no non-bonding electrons, 1 bond equals 0, right? So the way that we would draw that is we would put a little positive next to the oxygen, and you generally circle it when you're handwriting it. You don't necessarily have to circle it, but it does make it easier to see. So let's think about the differences of valence electrons versus formal charge. If you went ahead and go ahead and calculate or count all the valence electrons, what you'd see is that all the oxygens have an octet, and all the H's have a duet. Right, everything in all 3 of these structures has a filled valence shell. So all 3 of these are good valence or good Lewis structures, right? Because having a filled valence shell is more important than having a low formal charge. When it comes to formal charge on Lewis structures, the closer to 0, the better. When you're deciding between different Lewis structures, which one is better, but sometimes it's unavoidable. Right. For example, in all 3 of these structures, the 2 that have charges, there's no other way that you could draw them so that they didn't have charges. And it makes sense, right? We learned hydroxide as one of our polyatomic ions, and we know that it overall has a charge of -1, and there's that negative charge right there. The charges are always going to be +1, 0, or -1, right? So if you see a charge, something other than that, a +2, -2, chances are you're doing something wrong. And I'll put an almost here because there's no rules in chemistry. And if there's a rule, there's definitely an exception. But for our course and for Gen Chem and even OChem, you'll never see a formal charge that's greater than ±1 unless it's on a transition metal. Let's do one more example. Right, here's our ammonium, our NH4. And if you think about the polyatomic ion that you memorized, it has an overall formal charge of +1. So let's see where that +1 charge comes from. If you think about the hydrogens, we did a bunch of examples of these. When hydrogen has one bond, it's neutral. So let's check out the nitrogen. Nitrogen is the first element in group 5, so it has 5 valence electrons in its lone state, has no bonding or non-bonding electrons here, and then it has 4 bonds for a total charge of +1, right? So that's where the positive charge ammonium comes from. It comes from that nitrogen. And what that tells us is if this ammonium reacts, it's probably going to react in such a way that this nitrogen goes from being a +1 formal charge to a 0 formal charge. Overall, you should get really good at identifying formal charges. This is something that should be a very quick and easy process.